This time, based on examples of calculation, I will explain calculation procedures and methods. Introduction. The first step for air conditioning design is to calculate heat load calculation. Recently, calculation software is often used to do so. Such calculation software is convenient, and anyone can easily calculate using it. It is, however, dangerous to use it without knowing the background of the calculation. You may get caught in an unexpected trap. The purpose of this section is for you to understand methods of basic heat load calculation. Heat loads, simply put, are classified into various types, as I explained in the basic section of the heat load calculation. The heat load calculation explained here uses loads involved in the thermal room load. A model for heat load calculation is shown on this slide. Let's calculate the heat load for the manager's office located on the second floor. First, based on documents including the special specifications, confirm and determine conditions for air conditioning. Confirm the name of the building and its location. Based on the document including psychrometric charts, determine room temperature, relative humidity, enthalpy, and absolute humidity as conditions for air conditioning in the rooms. Fill in a predetermined table with them. For outdoor conditions in the summer, determine the maximum temperature and temperatures at 9 a.m., 12 noon, 2 p.m., and 4 p.m. For such conditions in the winter, determine the minimum temperature for design. Determine relative humidity, enthalpy, and absolute humidity at the same time. The reason why summer conditions are divided into different times of the day is that acquisition heat loads are different depending on the direction. If you know the minimum temperature in the winter, you can consider it to be the maximum heating load. You need not therefore classify temperatures based on different times of the day in the winter. Determine outdoor air conditions based on the time of day, referring to various literature including the handbook. Furthermore, you can obtain the outside air temperature of each time of day by using the approximate equation. Confirm the direction of the building based on building requirements. We check building direction from layout drawing plan, building design, document, and others. Japan is located on the Earth at north latitude 30 to 40 degrees. This is one basically condition. Normally in Japan, building design is done by consideration of setting south face. We have much meaning east, west, south, north direction for building. It is required to be checked detail building direction, but not about rate. Confirm the specifications of walls, floors, windows, ceilings, and the roof. Based on each part, calculate the coefficient of overall heat transfer. The calculation formula is shown on the slide. The calculation method was already explained in basic heat load calculation for air conditioning system. Based on the document including the completed chart, confirm the structures of individual parts of respective rooms. Calculate the coefficient of overall heat transfer based on them. Determine the heat conduction of required construction materials while referring to data including the various literature. For calculation of coefficient of overall heat transfer, see the table on this slide. Let's practically calculate heat load. First, let's calculate the heat load caused by a window pane. Types of heat load caused by a window pane are heat transfer load and solar load. Let's individually calculate those load. The calculation formula of the heat transfer load is shown in this slide. The coefficient of overall heat transfer was already explained. Determine the window area based on the external size of the sash. The temperature difference is that between the inside and outside of the room. Now, let's calculate solar load. The calculation formula of the solar load is shown on this slide. Determine the solar heat gain factors based on documents including those found in literature. Confirm the location of the building and its direction. In this example, the location is Tokyo. The building faces south. Determine the shading coefficient after confirming the type of the glass and the presence of window blinds. Here, the type of the window pane is clear glass. Bright-colored window blinds are used. Fill in the table with required numeric values and use them for calculation. Examples of various group values are shown in the table. Results calculated in conjunction with the window pane are shown in the table. In the upper cells, the results of calculation of the heat transfer load are shown. In the lower cells, the results of calculation of the solar load are shown. Next, let's calculate the heat load caused by outside walls and roofs. The calculation formula of the heat transfer load is shown on this slide. The temperature difference of this calculation is very different from the temperature difference calculated for the previously mentioned window pane. Outside walls and roofs do not allow the sunlight to pass through, but they are affected by solar energy. Solar energy hits the walls and acts as a heat load. Outside walls and roofs have large heat capacities, so the solar energy acts as a heat load after a delay. The equivalent temperature difference is used for calculation. The equivalent temperature difference depends on the types of the walls. As described above, the degree of the effective heat is changed. Consider the structure of the building to determine the wall type. Types of walls are classified as shown on this slide. Here, the thickness of the concrete is 150 millimeters, and that of the insulation material is 25 millimeters. So, the wall type is number 3. Look up the equivalent temperature difference in the table after you have confirmed the type of the wall. On the slide, the table of the equivalent temperature difference in Tokyo is shown. In this table, the standard room temperature is specified. if the actual room temperature is different from the standard value, correct it. Numeric values shown in this table are based on an assumed room temperature of 26 degrees Celsius. Now we have set the room temperature for design to be 28 degrees Celsius. Numeric values determined by subtracting 2 degrees Celsius from the values of temperature shown in this table are equivalent temperature differences at individual times. Values of the outside wall are organized in the table. Here, the temperature difference in the winter is the difference between the temperature in the room and that outside of the room. Correct the effect by the seasonal wind by using a directional coefficient. The results calculated for outside walls are shown in this slide. Let's calculate heat loads caused by inside walls. The calculation formula to use is as shown on this slide. Durability of the dimension to calculate an area and the temperature difference are different from those for outside walls. As shown on the slide, the temperature difference is determined by multiplying the coefficient by the temperature difference between the temperature of an air-conditioned room and that of a neighboring non-air-conditioned room. If the next room is air-conditioned at the same temperature, you do not have to calculate the loads caused by the inside walls, because the inside walls do not cause heat loads. Here, the northern quarter area is not air-conditioned. The temperature difference coefficient is 0.4. Required numeric values are organized for the heat load of the inside wall in the tables, and results are also shown in the lower table. This is the end of the explanation about external heat load, construction framework load. We prepared some materials for calculation including this page and the following pages. Conditions are summarized in this table. This slide is used for the calculation of the coefficient of overall heat transfer. You can see the heat load calculation format on the slide. Now, let's calculate the heat load caused by internal heat generation. Internal heat generation loads include people loads, lighting loads, equipment loads by appliances including OA equipment, as explained in the basic section of the heat load calculation. First, let's begin calculation of people loads. Calculation expressions for heat loads caused by people are shown on this slide. Select calorific values from the data in the tables based on operation conditions and room temperature. In most cases, at the planning stage, the number of people is uncertain. Calculate the number of people in the room by using data of occupied areas or personnel density. Let's calculate lighting loads. A calculation formula for heat loads caused by lighting is shown on this slide. Calculated after confirming factors including the intended use of the room, the planned lighting intensity and the type of lighting equipment. As less consumption power is used for equipment due to changes from low consumption type fluorescent lights to inverter fluorescent lights, less heat is generated by fluorescent lights. The focus of office work changed from document-related tasks including writing and drawing to tasks by which computers are used. Some companies, therefore, tend to adopt smaller planned lighting intensities. Refer to relevant special specifications and design drawings. Next, let's calculate the appliance calorific value and the equipment calorific value. Calculation equations to determine loads caused by appliance heat generation, namely so-called electric outlet loads, are shown on this slide. Based on design conditions and the intended use of the room, determine the load. The consumption power is often set from approximately 30 watts to approximately 60 watts per square meter, because OA equipment has been used in many cases recently. For some buildings, including data centers, over 300 watts of consumption power per square meter may be expected. If, particularly, equipment with large consumption power is installed, you need to add other values. For buildings including factories, process equipment is mainly used. So, the large portion of the generated heat is caused by process equipment. Heat loads are caused throughout the year. A room with process equipment, therefore, is cooled throughout the year. Therefore, consult with the customer in charge about heat loads, make a list of process equipment, and organize it in a table. Some process equipment may not be fully operated. Consult with the customer in charge about required data, including operating ratios of individual process equipment. In addition, calculate equipment heat loads. If the internal heat load is calculated based on calculation of people load, lighting load, and equipment heat load, you will obtain results like that in the upper table on this slide. In the table at the bottom, numeric values to be used for calculation are organized. You should leave those numeric values as basis for calculation. For example, you can use them in calculation formats. In addition, you can use them in tables. If you prepare load calculation formats, add up the individual loads. Consider the total load to be the load of the target room. For the sensible heat load at 9 a.m. in the summer and that in the winter, set an allowance of approximately 10% for correction at the start during intermittent operation. For correction values to consider the heat load of the duct surface and air leakage, you may estimate an allowance of approximately 10% S. For correction values to consider the load caused by fans, you may estimate an allowance of approximately 5%. Here, the load at 9 a.m. in the summer and the load in the winter are multiplied by 1.1 to estimate an intermittent operation coefficient. As explained in another course, if you select systems, estimate a few percentage points for allowance coefficients. If allowances of correction values for various appliances are set too large, you will, in the end, select systems that are too large as a result of the heat load calculation. By understanding what load should be estimated for allowances, calculate the total load. The skin load in the heat load calculation format is the heat load obtained from a perimeter zone. If you treat loads caused by perimeter zones, such loads are considered to be heat loads. by using the basic unit of heat loads determined by dividing heat loads by floor spaces. Check the approximate values. Numeric values as shown in the table are reference numeric values. As a calculation example, the maximum air conditioning cooling load is 5,502 watts, with the floor space being 56.3 square meters. The approximate value is approximately 98, which is around the mean value. Calculate heat loads of individual rooms to be air-conditioned in this way, and based on those results, select heat source equipment and air conditioners. This is the reason why I said that the first step of design for air conditioning is to calculate the heat loads. If the intended use of the room is changed, and the tenant is to carry out engineering or construction work, you can use calculation formats for such engineering work as basic information to calculate heat loads. Be sure to completely understand the calculation methods. This is the end of explanation of example heat load calculation for air conditioning system.